The following moles and titration question, taken from an ATP O-levels past paper, deals with finding the water of crystallization, which is X over here in this hydrated salt. So you need to find the water of crystallization. And the question reads that you're given washing soda. He's saying the washing soda is hydrated sodium hydrogen carbonate. So this is your ingredient in which you have to find this value, where X is given as a whole number. And a student determines the value of X in the formula by titration with 0.1 mole per decimeter cube hydrochloric acid. So there is another solution which is 0.1 mole per decimeter cube hydrochloric acid, and that solution is called S. So let's start with the steps. The first thing that he does is, in part A, a sample of sodium carbonate .xH2O, this hydrated salt, is placed in a previously weighed container, which is then reweighed. So the mass of the container plus the salt is given. It's given as 8.31 grams. And the mass of the container is also given, which is given as 4.79 grams. And you are asked to calculate the mass of sodium carbonate hydrated salt, the crystal with water in it. So the simple thing that you need to do is you need to subtract the mass of the container from this value 8.31. So if you get rid of the mass of the container, you'd be left with the mass of the hydrated salt. So I'm going to subtract 8.31 with 4.79 grams, and the answer that I'm going to get is going to be 3.52 grams. So that is the mass of, and I'm going to write this over here, the mass of the hydrated salt, sodium carbonate .xH2O. We're still not sure what X is. So the mass that is being taken of this hydrated salt is 3.52 grams. So that's the first thing. Now moving on to part B. In part B we have the student transfers the sample of sodium carbonate .xH2O to beaker, adds about 100 cm cube of distilled water and stirs the mixture until all the solid has dissolved. And the contents of the beaker are then transferred to a volumetric flask, and the solution is made up to 250 centimeter cube with distilled water. So he's adding distilled water, and this is now called solution T. So let's sketch all the steps that are being performed in this paragraph over here. So here I have drawn this beaker over here, and I'm going to transfer, this is the first step. He transfers, let's underline that, sample of sodium carbonate .H2O to beaker, and then adds about 100 cm cube of distilled water and stirs the mixture until all the solid has dissolved. So that's the first thing we're going to do. We're going to put this in the water and add 100 cm cube of water. Now when you add 100 cm cube of water, remember sodium carbonate, it's a group 1 compound, and it's probably very soluble. So we're making a solution. He's stirring and the mixture until all the solid has dissolved. So eventually all this sodium carbonate is going to be dissolved completely, and you're going to get sodium carbonate Na2CO3 that would get converted. Once all the salt is dissolved, now it's going to be in aqueous state. All the water of crystallization would be lost because that's going to mix with all the other water molecules, and you would simply be left with sodium carbonate in aqueous state. Now once all the solution is made up, the next part of the question reads that the contents of the beaker are then transferred to a volumetric flask. So let's underline that beaker are then transferred to a volumetric flask. So we're going to transfer the contents to this volumetric flask that's drawn over here. And the solution is then made up to 250 cm cube by adding with distilled water. So you're going to add distilled water and make a 250 cm cube solution. So you're going to add more water to it. Once you add more water to it, the volume of the solution would increase. You're going to dilute the solution. Eventually, all the sodium carbonate would now be present in a 250 cm cube solution. And the name of this solution, this is solution T. So he's given the name of the solution as well. Now this is T. And what does T contain? It contains the same sodium carbonate that's dissolved, only that the solution is now more dilute. It's a bigger, the solution has more volume because you've added a lot of distilled water to it. So now this is sodium carbonate aqueous after being transferred to a volumetric flask and after adding distilled water to it to make a larger volume, a 250 cm cube solution. So we've diluted the solution. In the next part, the last part states that the 25 cm cube of T is then transferred to a conical flask. So we would now transfer 25 cm cube of T into a conical flask. So over here is the conical flask that I've drawn, and 25 cm cube of T is transferred to a conical flask. So this T over here, this 250 cm cube solution, now we're going to take only 25 centimeter cube T. So 25 centimeter cube T is transferred to this conical flask. Let's show this 25 cm cube T. What does T contain? It contains the same sodium carbonate in aqueous state, the dissolved sodium carbonate in aqueous state. So that is present in this flask over here. And he's asking us to name the apparatus used to transfer this volume of T. Now, whenever you're transferring solutions from one container to another container, and especially when the volume is 25 cm cube, the best apparatus to do that is going to be a pipette. A pipette is a suction device that fills up when the liquid is sucked into the pipette, and then it is released in a separate container. So pipette is used. It's very accurate for measuring 25 cm cube. So you're going to pipette and transfer 25 cm cube of sodium carbonate into this flask over here. In part C, moving to part C, a few drops of methyl orange indicator are added to the conical flask. So you are adding a few drops of methyl orange to this flask. Now this methyl orange is added. Now methyl orange is an indicator. It is red in acidic condition, and it's orange yellow in alkaline conditions. After doing that, let's underline that a few drops of methyl orange indicator are added to the conical flask. After doing that, S is now put into a burette and added to the solution in the conical flask. So we're now going to draw a burette over here. So here is my burette, and S is put into a burette. Remember, S was the 0.1 mole per decimeter cube hydrochloric acid. Let's confirm what S was mentioned very initially in the beginning of the question. Let's go back and see where S was mentioned. So here it is mentioned 0.1 mole per decimeter cube hydrochloric acid solution S. So it's 0.1 mole per decimeter cube of hydrochloric acid, which is put into the burette over here, and this HCl is then slowly added to this conical flask which contains sodium carbonate. Remember that acids would react with carbonates. Acids and carbonates react to produce salt, water and carbon dioxide. So they're going to start reacting once you start pouring HCl into this conical flask. Now the next part is you have to tell what is the color of the solution in the flask before S is added and at the end point. Now one thing that you must know is that sodium carbonate is an alkaline, it's a basic salt. So since it's a basic salt, it's a slightly basic salt. Since it's a basic salt, so the initial color of this flask is going to be, it's going to be orange yellow, because methyl orange would have orange yellow color in alkaline condition. And as soon as you start adding HCl would start reacting with the sodium carbonate. It would start neutralizing it. All the sodium carbonate would react, sodium chloride would eventually form. So all the sodium carbonate would react with the HCl, and a neutralization reaction occurs. Eventually a point would come when all the sodium carbonate has completely reacted. So the sodium carbonate molecules in this flask over here are completely finished. And if you keep on adding HCl beyond that point, the solution over here would start becoming acidic, because the HCl has nothing to react with. And that is the end point when HCl goes in excess. So when HCl, even a few tiny drops of HCl are added beyond the required amount, the solution would become acidic, and methyl orange has a red color in acidic condition. So that would indicate that the reaction is now finished. All the sodium carbonate which was present in the flask has been used up. So that would indicate that you should turn this tap off. So before S is added, the color would be, it would be orange yellow or closer to yellow, and at the end point when the acid goes in excess, the color of the solution would become, it's going to become red. Moving to part D of the question, the student now does 3 titrations. The diagrams below show parts of the burette with the liquid levels at the beginning and end of each titration. So he's basically, at this point over here, he's now started titration. He's adding HCl into this flask, and he does 3 separate experiments. Remember, 3 separate experiments are done to improve accuracy, because if you do more experiments and you take the average value, the average would be more accurate compared to an individual reading. So 3 separate titrations are done, and we are basically interested in what amount of HCl is being added to neutralize or react with the sodium carbonate that's present in the flask. So we need to figure out the volume of HCl that's being added, and he's drawn the burette. He's given us a picture of the burette for example, this is the first titration, and this is the initial burette reading and the final burette reading for the first titration. And the initial reading is 0.00 centimeter cube. So there's a table given over here as well, and we need to fill that table. And the final burette reading is 25.60 centimeter cube. Now the amount of HCl that's being added to the flask is going to be the difference between the two values. So this was the burette initially that was filled to the 0 centimeter cube mark. Now it's filled to the 25.6 cm cube mark, which means that the difference, that's the amount of HCl that has actually gone into the flask over here containing sodium carbonate. So we're going to take the difference, the volume of S. Remember, this was solution S, the HCl 0.1 mole per decimeter cube. HCl, this was solution S. So the volume of S that's being added is going to be the difference between the two values. So in the first case, it's going to be 25.60 centimeter cube. Moving to the second titration, the initial burette reading is it's 3.50 centimeter cube. So that's your initial burette reading, 3.50 centimeter cube, and your final burette reading is 28.20 centimeter cube. So that's your final burette reading, 28.20. And in the second titration, the volume of S that's being added is going to be the difference between the two values. So if you subtract 28.20 from 3.50, the answer that you're going to get on your calculator, it's going to be 24.70 centimeter cube. Remember to note down burette values to 2 decimal places, because that's the accuracy of a normal burette. So remember to note down these values to 2 decimal places. Moving to the third titration, you have the initial burette reading is 11.40 centimeter cube, and the final burette reading is 36.30 centimeter cube. So that's your final burette reading. So the amount of 36.30, so the amount of HCl that's added, or volume of S that's added in the third titration, is going to be the difference between these two values, which comes out to be equal to 24.90 centimeter cube. Now moving to the next part, we've noted down the values, and these are the volumes of S that were added in each of the titrations: 25.60, 24.70 in the second, and 24.90 in the third titration. Now we need to take the best titration results, and remember, the best titration results are the ones that would be close together. So these two values are close to each other, whereas this is slightly off, it's slightly further away from, so that indicates that there must be something wrong in this experiment. More consistent values that are close to each other indicate that the titrations are accurate. So these two are my best titration results, and based on these two titration results, I now have to, using these results, I need to calculate the average volume of S that's used. So I'm going to pick these two results, 24.7 and 24.9, and I'm going to take out the average, which is going to be 24.70 plus 24.90, and I'm going to divide that by 2. If I divide that by 2, the average volume of S that's being used in the 3 titrations is 24.80 centimeter cube. So, and I'm going to add that to my sketch over here as well, adding that. So the volume of HCl that's used, the average volume of HCl that's used is 24.80 centimeter cube. So that's the average volume of S that's being used. Moving to the next part, in part E, you're now asked that he's given us that S is 0.1 mole per decimeter cube hydrochloric acid. We now have to calculate the number of moles of hydrochloric acid, the average volume of S from D, which basically means we now have the concentration of S, which is given 0.1 mole per decimeter cube, and we also have the average volume of S, which is 24.80 cm cube. So if you have the volume and you have the concentration of a particular solution, you can find the moles of HCl that are being used on average in the titration. So the volume is given and the concentration is given. The formula for moles for a solution are concentration multiplied by volume, and the concentration given is 0.100 multiplied by the average volume, which over here is 24.80, but it's in cm cube, so I need to convert that to dm cube. So I would divide that by 1000, and the answer that I'm getting on my calculator for this is 0.00248 moles. So that is the amount of moles of HCl that were added from the flask. So I'm going to add that as well to my sketch. So it's 0.00248 moles of HCl are used in, on average, are being added from the burette, and let's highlight that as well. So I've circled that. That's the amount of HCl that's actually going into the flask over here. In the next part, part F, the question states that 1 mole of sodium carbonate reacts with 2 moles of hydrochloric acid. So he's given us a ratio that the ratio of sodium carbonate with respect to hydrochloric acid, the ratio is that 1 mole would react with 2 moles of HCl. So the ratio is 2:1. Now I can show that on the picture as well over here. What the question states is that 1 mole of HCl over here, let's underline that, highlight that. If you have 1 mole of HCl, let me correct that. If you have 2 moles of HCl, then 2 moles of HCl would react with exactly 1 mole of sodium carbonate. So that's the ratio in which they're going to react. So if you have 2 moles of HCl, then 1 mole of sodium carbonate would react with it. But we have 0.00248 moles which were calculated in the previous part. So according to this ratio, the moles of sodium carbonate can be calculated. So calculating the moles of sodium carbonate, the ratio is, let's clearly write down the ratio over here, Na2CO3 to HCl. The ratio in which the two are reacting is 1:2. So if you have 0.00248 moles, if you have 0.00248 moles of HCl, we calculated the moles of HCl in the burette in the previous part, 0.00248 moles of HCl, and how many moles of sodium carbonate would react with it? And we can use simple ratios, cross multiply this, and x would come out to be equal to, it would come out to be equal to 0.00248 divided by 2, and the answer is going to be 0.00124 moles. So that is the amount of moles of sodium carbonate in this flask over here, 0.0012. So it's 0.00124 moles. And let's highlight this as well. This is the quantity of sodium carbonate that is present in this flask over here. Now moving to part G, which states that using your answer to F, which is the previous part, calculate the number of moles of sodium carbonate in the 250 cm cube of T. So this 250 cm cube T is the original sample of T that we made over here. This is the 250 cm cube solution of sodium carbonate aqueous. So we found the moles. Remember, we took 25 cm cube of T in this flask, and we found out the moles of sodium carbonate, which came out to be 0.00124 moles in this 25 cm cube sample. Now we're being asked to figure out what are the amount or quantity of moles in this 250 cm cube sample. So if in 25 cm cube you have 0.00124 moles, so in 250 cm cube, that's 10 times the volume. The number of moles would also be 10 times. So according to the ratio, the number of moles of sodium carbonate which is over here, would be multiplied by 10. That would be the quantity of moles of sodium carbonate in this flask over here, because the volume 250 cm cube is 10 times the volume of 25 cm cube T that's being used over here. So again, using ratios, we know that the 25 cm cube T in the flasks, in the conical flask, contains how many moles? It contains 0.00124 moles. So the original sample, which was 250 cm cube T, since the volume is 10 times, the number of moles would also be 10 times. So it's going to be 0.00124 multiplied by 10 according to this ratio, and the answer would be 0.0124 moles. So that is the amount of moles of sodium carbonate, 0.0124 moles of sodium carbonate. Let's highlight that as well. That is the amount of moles in this flask over here. And remember, these are the moles that were coming from this sample. When you dissolved this sodium carbonate 3.52 grams of hydrated salt into this flask, and then you transferred that solution into this flask and added distilled water. So this is the quantity of moles of sodium carbonate in this original sample of this salt. So in the next part, you're now asked to calculate the relative formula mass of sodium carbonate Na2CO3. So the first thing is we need to find the MR. The MR of sodium carbonate is going to be the two sodiums. So he's given all the atomic masses over here from the periodic table. So there are two sodiums, so that's 23 into 2. There is one carbon, which is 12, and there are three oxygens, that's 16 into 3. So if you sum them up, it's going to give you a value of 106. So that is the MR or formula mass of sodium carbonate. And then moving to the next part, is saying that using your answers to G and H, the previous steps, calculate the mass of sodium carbonate 250 cm cube of T. So we found the moles. Now we found the moles of sodium carbonate in this 250 cm cube sample. We also have the MR now, which is 106. So if you have the moles and you have the MR, you can find the mass. Mass is basically equal to moles multiplied by the molar mass, which is the MR or formula mass. Now the moles are 0.0124 moles. That was the amount of Na2CO3 in this flask over here. So we have the moles. We're going to multiply that by the molar mass, which is 106, and the answer that I'm going to get is going to be 1.31 grams. If using my calculator, the answer that I'm going to get is 1.31 grams. So that is the quantity of Na2CO3. That is the mass of Na2CO3 in this volumetric flask. So it's 1.31 grams. And remember, all this sodium carbonate is coming from this original salt that we dissolved. So moving to the next part, you're now asked, by subtracting your answer in I from your answer in A, calculate the mass of water in the original sample of the hydrated sodium carbonate. So moving back to our sketch, our original sample of sodium carbonate was a hydrated salt. The mass was 3.52 grams. Since it was 3.52 grams, it also contained a lot of water in it. There were water molecules also added to it. Now, using titration, we were able to figure out the moles of sodium carbonate, and we were able to figure out the mass of sodium carbonate. So we have the mass of sodium carbonate in that sample, that's 1.31 grams, and we have the total mass of the salt, the original salt that we took, that was 3.52 grams. So if this salt contains 1.31 grams of sodium carbonate, then how much water would be contained in this salt? So we just need to subtract the two values. So subtracting the two values, it's going to be 3.52, which is the total mass of the salt with the water in it, minus 1.31 grams, and that which is the mass of sodium carbonate. If I subtract the two values, the mass of water can be found, which is coming out to be equal to 2.21 grams. So that is the amount of water in this hydrated salt. It's 2.21 grams. So the total mass was 3.52, 1.31 grams was sodium carbonate, so 2.21 grams is the water in this hydrated salt. In the last part, part K, using your answers to H, I and J, our previous three answers, in the following formula, calculate the value of X and write the formula for hydrated sodium carbonate. Now, you don't really have to do a lot of thinking. You just they've given you a formula for finding X, so you just plug in the values. You just need to plug in the values. So X would be, what was your answer to H? So let's go back and have a look at our answer to H, which was 106. So that is 106 multiplied by our answer in J, which is 1.31. So that's the answer in J is this part, it's 2.21. So it's 2.21 divided by, you're dividing it by 18, then multiplied by the answer in I, which is this answer over here, which was 1.31. So I just plugged in the values, and now using the calculator, the answer that I'm going to get is approximately equal to three significant figures. It's going to be 9.393. And since in the very first beginning part of the question, it was stated that X is a whole number, so we need to round this value. So if I round this value, this answer would be approximately equal to 10. So we now have to figure out the formula of the hydrated sodium carbonate. This means that the formula is going to be Na2CO3 dot XH2O. Now X is 10, so that would be 10H2O. So that is my salt. There wasn't a lot of thinking or understanding going in this last part because he gave you this formula, so you just need to plug in the values without worrying about how X is found. So we are able to find X using this formula, which comes out to be equal to 10. So this hydrated salt, for every 1 sodium carbonate, there are 10 water molecules in the crystal of this hydrated salt.